This brings us to the other important application for electrolysis, the splitting of water to produce hydrogen and oxygen. This reaction turns out to be extremely important for people living off the electrical grid because it means that sunlight can be brought directly onto a photovoltaic cell, and that voltage can either drive a lighting system or it can drive a chemical reaction to produce a fuel. And that chemical reaction is two water molecules converted to O2 and two hydrogen molecules. So we can do this either way. We can, in fact, there are a number of ways. Anytime we want to generate hydrogen, we can use a photovoltaic cell, but we can also use a battery because all we care about is that we're providing a voltage that will split water apart. Now, if I take this particular example and I look at what's coming out, I can see that twice as much gas is being produced at one electrode as it is in the other. But by inspecting that chemical reaction, I see that anytime I split water, I produce two molecules of hydrogen and one molecule of oxygen. So I know immediately that this is hydrogen and this is oxygen. I can do that by inspection. But now let's look at more detail at what these actual reactions are. And this is one of the most interesting aspects in all of electrochemistry because it turns out that splitting water is crucial to almost every process in nature, including living organisms, but in particular photosynthesis that produces all of the organic material across the globe. And that organic material is created literally from CO2 in the atmosphere and water, and it produces organic structures and oxygen. And it's one of the most crucial reactions for the sustaining life on the planet. So now we're ready to dissect exactly what's going on in that reaction, the reaction where we couple the battery into two cylinders that can capture the gases coming off of the electrolysis of water. And we noticed last time that we had one cylinder that was capturing hydrogen, and we had the other cylinder that was capturing oxygen, and we were capturing two molecules of hydrogen for every one from O2, because when we break O2 apart, we form H2 and O2, but that means that we have to balance this by multiplying H2O by 2, and that drives the stoichiometric coefficient for H2 to 2, and that's why we have two hydrogens for every oxygen molecule coming out. All right, well, we also know that the battery, with its negative charge, is going to send electrons away because electrons are repelled by a negative potential. And that means that electrons are flowing into this cathode. That means immediately that reduction is taking place in this right-hand cathode. So reduction, what is the reduction of water? So let's write that reaction because it's so important. The reduction of water means that we're taking water, and we'll just put the stoichiometric coefficients in here to economize. We're driving electrons into water, and the product side is H2 and 2 hydroxide anions. So that's the reduction side. Now, the other electrode has electrons flowing out of it because those electrons have to flow into the positive terminal of that battery. And that is the extraction of electrons, and that's oxidation. So now, simply by inspection, we've identified the reduction and oxidation reactions, and the oxidation of water is 2H2O, and the product of that are electrons and oxygen and protons. And this is an extremely famous example. It's called the water splitting reaction, and that is the reaction that's central to all photosynthesis globally. So we owe that reaction a great debt of gratitude because it supplies literally all of the organic material growing across the globe. All right, But we also know, because we're now becoming experts in electrochemistry, that we have to balance electrons. And so in the reduction step, we've got 2 electrons. In the oxidation step, we have 4. So let's balance electrons, since we can neither create nor destroy electrons in an electrochemical reaction. But now we're ready to add these 2 together, because we're now going to be canceling the 4 electrons on the product side of this with 4 electrons on the reactant side, because we're multiplying by a factor of 2. So when we add all this up, this gives us 6 waters on the left-hand side. And on the product side, we have 2 hydrogen molecules. We've got an oxygen molecule, and we've got 4 hydroxide anions, and we've got 4 protons. But now look at what we have on the right-hand side. We've got 4 hydroxide anions and 4 protons. That gives us 4 molecules of water. We've got 6 on the left-hand side, 4 on the right-hand side. That means that 2 waters are all that's left in that net process, and all we have left on the right-hand side are 2 H2 plus O2. So by the input of an electrical potential, and we can generate that with a battery, we can generate with a photovoltaic panel, we can hand crank a generator, we can produce hydrogen that's then a fuel that can be fed either into a flame to cook, or we can feed it into a fuel cell to produce electricity.